Hello everyone. So today we are going to see the new chapter which is rotational motion. So till now we have been concentrating our attention on the translational motion. What is the difference between translational and rotational motion, that we are going to see in this particular chapter, and then going to analyze this particular rotational motion in detail. So if you look at the type of bodies that we have been considering for now, which were discussed in the Newton's law chapter or work energy chapter, all those bodies were considered as point masses. So if you want to apply the three equations of kinematics, which is V is equal to U plus 8S is equal to UT plus half AT square, and the third equation V square is equal to U square plus 2AS, these three equations if you want to apply, you used to consider that a body is to be imagined as if it's all the particles of the body, they are moving together with certain velocity. So the entire body, let it be a body which is as huge as a car, or let it be a body which is as small as a rubber ball. Both the bodies were being considered as a point mass. So we used to consider that all the particles of the body, they are moving with the same constant velocity throughout the motion. We did not consider the individual differences in the velocities or the positions of the motion between these for these bodies. So in this chapter we are going to consider those differences. To illustrate what exactly I mean by here is, so if we consider that this particular ball is thrown with certain velocity from the ground and then it lands at this particular point. Now if I ask you, where at what distance will this particle land? Your answer will be the range of this projectile, which we solved it in projectile motion. But then I will ask you, the ball is not a small rubber ball, but it in fact is a football, which is relatively a bigger one. Then if I ask you at what distance will it end up, then you will say that it ends up at this and this particular distance. And then I ask you, which point of the ball does land here? Is it the rear point of the ball or is it the front point of the ball? Then you will say that we didn't consider ball to be a larger object, but instead we considered it to be a point object, probably concentrated at its center. So it is the center of the ball that lands here. But in reality, ball has certain dimensions. So a football is a bigger one. So it has its rear point, it has its front point, it has its top point and bottom point and center point. So these are 5 points. They are not different. They are not same point. They are all different points. So these different points, they can have their different motions, especially when you throw the ball with a particular velocity, and ball also has a rotation about its center. Then every particle of the ball will have different velocities, and such a motion is called as rotational motion. So the things change if you shift your focus from analyzing the bodies as particles. Right from there, if you shift your focus to the extended bodies, the things change. For example, the motion of a vehicle that I drew before some time, this motion of the vehicle, you used to consider this entire vehicle as a particle, but is that true? The wheels of the vehicle, they are moving with certain different velocity. The entire rest of the body of the vehicle is moving with some different velocity, because wheels, along with the translatory motion, they have a circular motion as well. So such a type of motion, which is a combination of translation and circular motion, is termed as a rotational motion. And hence, when the focus it shifts from particles to the extended bodies, basically the bodies which have length, width and height, all the 3 dimensions or probably 2 dimensions of this, when the focus shifts from a particle which has 0 dimension. So a particle, when we say a particle, we represent it with a point. So it doesn't have x or y or z direction. So there is no question of having any rotation about x axis or y axis or z axis. It just moves and it just describes a translatory motion. But if you talk about a football, or if you talk about a car, or if you talk about a ceiling fan, or if you talk about a giant wheel in a circus, then not all the particles of the body are moving with the same velocity, and that is why the focus of your analysis has to shift. If you really want to go closer to what is happening all around you, and if you want to analyze that, or if you want to analyze all the bodies that are described that are describing different types of motion around you, then your focus should shift from a particle to the extended bodies which you see in your day-to-day life. So that's the difference between a particle and an extended body. Now, what is a rigid body assumption? So while analyzing this, the rotational motion, we make an assumption that all the bodies that we will be analyzing will be rigid bodies. What is the meaning of a rigid body? Let us say, for example, you are analyzing a ceiling fan, or a table fan, or a giant wheel in a circus, or a potter's wheel, or say you are analyzing a spinning top. So in all these cases, all these bodies that I was describing are the rigid ones. Basically, the distance between any two particles of the body throughout the motion, that distance doesn't change. So I can mark any two particles of this body. Say one particle which is very close to the center, whereas the other particle which is far away from the center. If I measure the distance between these two particles at this instant of time, and then later after say a couple of rotations, if I measure the distance between the two, the distance has to remain the same. If that is the case, we call it a rigid body. So what is basically a non-rigid body? Let us say a body that starts rotating, the distance between the particles, it changes. Where is it observed? Not in the solids, but in case of liquids or gases, if we see a vessel which contains water in it. Okay, and if you start rotating this vessel, basically if you start, if you make this vessel move in a circular motion, then the water will arrange itself in such a way that it will look like a parabola. So this is a property that we will be discussing in the fluid statics chapter, not now, but just to show you what exactly is the difference between a rigid body assumption and a non-rigid body. So the particles of this particular fluid will arrange themselves in this fashion. So what has changed? Earlier, if you look at this vessel which was not rotating, the water was lying just steadily there at a horizontal level. If you measure distance between any two particles of water, it would be x. But now if you measure the distance between those two particles, it would be something else. So basically in this context, the distance between the particles, it changes for fluids as well as gases, and that is why under this chapter we will not be considering the motion of the fluids and gases, but we will be only considering the motion of the solids, and that to the solids where the distance between the two particles does not change. So here in this particular chapter, all the bodies that we will be considering will be assumed to be rigid bodies. So you consider a ceiling fan that I had drawn earlier, or you can consider your bicycle's wheel, or the tire of your car. You consider any such object. Now this particular bicycle wheel is moving forward as well as it is describing a circular motion about this particular axis. So if you consider any 2 points of this wheel, then the distance between these two particles will always remain the same. So you can consider this entire body as a rigid body. You consider any 2 points or any 3 points, they should not change the respective distances between them. Even the solids can have bodies which are non-rigid. For example, if you consider a solid object made up of rubber, a flexible rubber, and if you consider its motion, the distance between the two particles might change, maybe a very little, but it will change. So in such cases, they are not covered under this particular chapter of rotational motion. Whatever objects that we will be considering will only be rigid bodies. So that's all about the rigid body assumption that we'll be making. So you can cover any objects that you see in your day-to-day life. You can cover a stone under this particular chapter. You can have a potter's vessel under this chapter. You can have a bicycle wheel. You can have a ceiling fan or a table fan, or you can have a motion of a wooden object. Any object that is solid and the distance between the particles does not change, you can cover it under this particular chapter. Now, what is the difference between the translational motion and the rotational motion that I have been talking for so long? So you already know what is a translational motion. Translational motion usually is described with respect to 3 axes. So x-axis, y-axis and z-axis. A body can have either a one-dimensional motion along any one of these 3 axes, or it can have a 2-dimensional motion along any one of the planes out of these 3 planes, basically namely xy plane, yz plane or zx plane. So out of these 3 planes, the body can have its 2-dimensional motion in any one of these planes, or it can have 3-dimensional motion where its velocity vector will have components in x, y as well as z direction. So these are all the examples of translatory motion where all the particles of the body, they move in the same direction with the same velocity at a particular instant of time. So what does the word translational motion stand for? All the particles of the body. So let us consider this is our body, and this particular body is moving along this horizontal plane, or let us say we have this particular body which is moving down the plane. Then you consider any particle of this body or any particle of this body, all of them have the same velocity. Any particle, if you consider, every particle will, let us say, have 5 meter per second velocity, then each particle will have a velocity of 5 meter per second. Here, every particle, whatever velocity it has, let us say 7 meters per second, all the particles will have same velocity, same acceleration, same position, same displacement, everything will be same for all these particles of the same body. In that case, we call it a translational motion, which we have been discussing for so long. So in fact, we made an assumption that all the bodies that we are talking about are point masses. So inherently, we were assuming that there is no relative motion between any two particles of the particular body. So if at all we said that this particular ball, when it is thrown, it lands up at a distance equal to its horizontal range. In that case, we did not consider, or we did not take this possibility into account that the ball can have a spinning motion around its axis. So while the ball is moving forward, we did not consider that it might have a circular motion along its axis, along its central axis. We only considered the entire ball is only moving forward with certain velocity, but no possibility of spinning motion was considered. And that is why we were only dealing with the translational motion for so long. Now when rotation is brought into picture, this exactly is what happens. So along with this translatory motion, you will be having circular motion of all the particles around certain axis for a body. Just to understand what exactly is rotation, let us first consider an example of a ceiling fan. Okay, so this is how I look at the ceiling fan from the bottom. I see three blades of a fan, and when the fan it starts rotating in say clockwise or anti-clockwise direction, you have the axis of a fan which is fixed to the ceiling at a point. So the fan is literally not moving, or basically the fan is not having any translatory motion in the room. You don't have a fan which is at particular instant of time at this corner of the room, and then after certain instant of time then it is in the other corner of the room. This is not observed. For the entire time the fan is running, we see that it is fixed at the same location of the ceiling. But then can we say that the fan is not moving at all? Can we say that the fan is at rest? No, we see that the fan is rotating, but it's definitely not a translatory motion. The fan is not changing the position of its axis, but still we cannot consider it as a stationary one. We see that it is moving. Then what is this new type of motion called? It is called rotational motion. So that's a fundamental difference between translation and rotation. So you don't see a net change in the velocity of all the particles, but they have certain velocity along a common axis on the body, or maybe outside the body, which we will be considering different cases of such rotational motion later. Let us consider another example of a potter wheel. So you all know what is a potter wheel, right? You make pots and the wheel is fixed along a certain shaft. This shaft basically forms the axis, and you make different shapes of pots. Now a fundamental principle behind this potter's wheel is that its axis of rotation, it does not change. So it is always fixed at certain axis and it is rotating. So you can give a shape to the clay. You can put clay at any random shape over here, but when you touch your hands the clay and the wheel starts rotating and the clay starts rotating along with it, you can give it a shape. The reason behind this is all the particles inside this clay, they are describing a rotational motion along the axis. Now you might feel that the rotational motion and circular motion are one and the same, but that is not true. Circular motion, when we introduced circular motion, we considered that an object, a point object, is moving along a point in a circular motion. So if you look at the circular motion, the entire object was moving about a certain point, Whereas in rotational motion, different particles of the same object, they individually are describing a circular motion about an axis. So if you just consider different particles of this clay, this particular particle is rotating in its own circle. This particular particle is rotating in its own circle. A particle which is probably closer to the axis is rotating along its own circle. A particle which is far away from axis is rotating along its own circle of larger radius. Whereas in circular motion, all the particles of the body were having the same distance from the center of the circular motion. So if you notice it at any point of time, all the particles will always hold a constant distance from the center. So that was our circular motion, where individual particles, their motion was not considered. In rotational motion, individual particles motion about a particular axis with different radii of circular motion is considered, and that's a fundamental difference between a circular motion and a rotational motion. So you can consider this rotational motion about a fixed axis. Rotational motion about a fixed axis is basically circular motion of n number of particles of the same body. Rotational motion about a fixed axis is basically circular motion of n number of particles about a fixed axis. Okay, that's a rotational motion about a fixed axis. That means there is some other type of rotational motion as well, and that's a rotational motion about a moving axis. So basically, your ceiling fan, if you consider, is its axis moving? No, because we see ceiling fan stuck at the same position for so long. Even if you observe it after 1 hour, it is not going to leave its position. If you observe this potter's wheel, it is not going to change its position while it is rotating. So these are all rotational motions, but with fixed axis. The other type of rotational motion, so basically you have two types of rotational motion. The first one is rotational motion with fixed axis. The second is rotational motion with translation. So basically the axis is moving. So rotation with moving axis. Where do you observe such examples? The earlier example that I gave, a cylindrical object or a spherical object which is kept on the top of an inclined plane. If you release this object, every particle of the object will have a circular motion about the central axis. So all these particles, they are having a circular motion. If I just hold this object by putting a rod in it, and if I just hold it and rotate it, basically the motion will be like a wheel that is held at its shaft. So if I make a circular motion of this, all these particles will be having a circular motion about this fixed axis. Now if I just release this wheel, what will happen? It will travel down. That means the axis of the wheel is now not held at a particular location, but it is free to move. Then what will happen? After some time the wheel will be here. So the axis is moving. Along with the axis, every particle is moving forward. So every particle is having two types of motions. One is circular motion about a fixed axis, and the other one is motion of all the particles along with the body. So at this particular instant, if you observe this particle, it is here. After some time it is here. After some time the particle is somewhere here. Right? So the particle is moving forward as well as it is moving in circular motion. Such a type of motion where there is a combination of circular motion and translation is called as rotation with moving axis. So we will be dealing with two types of rotations. Rotation among basically rotation along a fixed axis, wherein you can cover your potter's wheel or your ceiling fan or a giant wheel in a circus. And the second one is rotation about a moving axis, where you can have a tire of a vehicle or a cylinder that is moving down the plane, or many such examples you can consider. So that is how we can describe rotation as a combination of translation and circular motion. So we'll be dealing with both these types of rotational motion in this chapter. So next lecture we'll be talking about the translational part of this rotational motion, where the center of mass, a new concept will be introduced. So all the body can be represented by a particular particle, which is a hypothetical one, but it is on the body. You can represent the entire body by shrinking it to a particular particle, that is called center of mass. So we'll be introducing this new concept of center of mass next lecture. Thank you.